Again, welcome to the last chapter, basically, as I was talking earlier, for this class. This is basically there will be more business down the road because we still have actually another exam to do on Tuesday next week. And there will be also another final on Thursday next week. And there are a few assignments that are still pending. So you guys, I'm hoping that you finish them and submit them too. So if you have any questions, please reach out to me. The review already for exam 4 is on Canvas. So I'm hoping that you guys take advantage of that review. As a matter of fact, it is graded as participation. Not so much so for the review for the final. As a matter of fact, the final for the review is going to be basically optional in terms of for you guys doing it or not, but it's still going to count separately. So you're urged still to do the review for the final. I did not publish the review for the final yet. There is still actually part of me, because usually I really don't like to assign stuff for the toward the week of the final, other than the actual exams themselves, namely the exam 4 and final. So there may be a possibility, depending on how it goes with the grades and so on and so forth, maybe we will do it also for participation. The reason why I'm saying that for the final is because some of you probably still need to really take that final and pass the class, because even if you don't, it's really a big chunk of the grade. So you really need to do that. So if all your concern is passing the class, some of you probably might get away with not doing it. But if you really want to get a good grade, you still have to take it. So you're still encouraged to do that. That's why I'm going to go look and everything and still probably make the review as graded, so that to encourage you to actually go and prepare for the final still. Again, this is in terms of the last stuff, in terms of business, so we still have a chapter to cover, so let's get to it. I know we've been doing basically astronomy in a sense. We did the solar system, previous chapters. Yes, exam 4 and the final are separate. Exam 4 is going to be on Tuesday. I mean, you know the plan. Basically, the exam will be open toward the evening, because some of you are working during daytime, so they need to start on the exam soon. And you have to understand also that these exams are not the same, so they are going to be different for different people. They're timed like anything else, and sorry, I'm looking at trying to say, I think something. And the final is going to be separate. Yes, the final is going to also open on Wednesday evening and close on Thursday next week. Thursday is actually when the start of the finals are going to be. So you have to submit it by no later than 10 o'clock in the morning on Thursday, December 10th. Okay, so the same plans, the same stuff. You may be given an extra half an hour for this final because of the sheer amount of questions you will have in it. So in order to finish everything and be done with it and submit your final. So the last half an hour actually is just for wrapping up and gives you a little bit of time to review your answers before hitting the submit button. So that's really the plan for what's going on in terms of exams. So Josh, to answer your questions, yes. Exam 4 is not the final. The final is separate from it. The only issue right now is the review for the final. If I open it too soon before exam 4, it might be confusing. In a sense, you still have a big exam to take care of. So I'm thinking probably I will open it sometime on maybe Friday. If I see a lot of people are doing the review for exam 4, then I will open it on Friday. If not, then I'll push it on Saturday. If not, then I'll probably push it to Sunday. And that's probably the last time we're going to have the review for the final is going to be available. However, it's going to close the minute the exam 4 is open. The review for the final, that is, to give you a chance to do your exam 4. And then it's going to reopen after that. Exam 4 should be at 10 p.m. on Monday, Christina. Okay, it should be available 10 p.m. on Monday. and ends at 10 o'clock in the morning on Tuesday. Okay, so this is in a nutshell everything. I'm hoping to follow up with this with an email, not an email, a message through Canvas explaining all of these things that I've been talking about. And I know, especially today, that because it's not graded, that some of you probably are going to opt out of basically looking at the recording. So I need to really send an email to those who are not really following, at least for the last lecture in here. Okay. Unless you guys have another question, then we're going to jump in. As I said before I actually started the recording, this chapter is not really long, so we hope to finish it. So we did the solar system, we did stars and the universe, and now we're going to get into a little bit of things that we can't see with the naked eye, okay? And those are coming from basically other studies that tells us, for example, the presence of dark matter and the presence of dark energy to explain some of the odd experiments we've been looking at. Okay, so these are facts; they are not fiction. Okay, so let me find the PowerPoint first of all that we need to do. This one. So again, we're looking at the structure of space-time. Space and time basically are the stage where everything is supposed to be happening, where everything, all the motion, all the objects can be located both in space and time. Because of the work of Mr. Albert Einstein himself, basically we were able to see that these two are actually connected, interconnected. We used to believe that time is an absolute parameter. It's true, it's the same everywhere in the universe. So the time for my watch and the time for your watch is going to be the same. However, his earlier, basically what started as thought experiments suggested that this may not be the case, because if two travelers are moving with two different basically velocities, the time is not going to be the same for both observers. So in this case, time is not the same. So that's one of the conclusions. It turns out that the experiments actually confirmed that. So the two together, namely time and space, they become one on basically part of one another, called space-time continuum. And space converts into time and time converts into space. In other words, time is nothing but just another dimension in this whole thing. Okay. Having said that, that leads to a different perspective on physics, and it comes up with explanations of the things that we've been looking at. For example, the path of the different planets around the sun, instead of being explained as due to the force of gravity, which is attracting planets toward the sun, we think of it differently. We think that the sun, or any masses that have, for that matter, including the Earth and everything else, what it does, it deforms space-time continuum. The mass is like a big, heavy ball of any object, it doesn't matter, sitting, for example, on a flat surface, like for example on a stretched sheet, for example. Then if you put a mass on it, it's going to create an indentation, and it's going to bend it. Okay, and depending on how big the mass is, the bending will be bigger and bigger on it. So that's basically, so what these masses are doing, for example, the planets, they're just following, trying to basically stay in orbit around this deformation. Okay, so there is no, so the sense of force now is really lost in this new approach. Okay, so what we used to believe that there is this causality of force and acceleration and all of that comes fundamentally, when it comes to the picture of the theory of relativity, is pure geometry. So geometry is the one that dictates everything. Okay, and that result from Mr. Einstein leads to, first of all, it coincides with all of the studies of the people before him, including Newton, including Kepler, and everybody else. So all of those observations that were done were confirmed by relativity. But as I said before, if a theory, all it does is explains what everybody have seen before, it's useless. It has to go a step beyond. One of the things that was problematic in the old days based on Newton's perspective, was the motion of Mercury. Mercury has a precession that no theory from Newton or before actually Einstein could explain. So the relativity was able to, first of all, confirm everything that was observed before. In addition to that, explain this and come with an accurate basically measurement for the precession of planet Mercury, because it's too close from the sun, and the deformation of space-time continuum around the sun is very great near it, so that leads to changes in the time measurements there, which leads to that precession. So that explains it. There was other confirmations, of course, in the 1919 solar eclipse also. One of the conclusions of relativity is that light will bend under gravity. So if we look at a star, and that star sends its light, and light goes around the sun, it's going to bend. The problem with it is we cannot see it during daytime because stars are not visible during daytime. During a solar eclipse, though, the sun is basically shielded for a moment by the moon, so the sun is covered, so the stars behind the sun, we can see them, and actually measurements for the bending of light was actually measured in tremendous accuracy with the theory of relativity. So this thing that we're talking about, space-time continuum, has been confirmed in the laboratory. This is not science fiction. Okay, this is stuff that is grounded in experiments and observations. So the theory of relativity is a strong and solid theory that first of all confirms everything that Mr. Newton has done and the people before Einstein have worked on in terms of gravitational observations and how the universe works and all of that, but it goes beyond that. It explains things that Newton could not explain. So that is really the advantage of it. So it's far more robust and stronger theory than the things we've been doing so far. Okay, it explains the supermassive, the super fast, and that is what the advantage of it is. If you're small stuff, for example, an apple falling on the earth, or the moon going around the earth, or even the earth being attracted to the sun because of the sheer distance, the bending of space-time continuum is very, very minimal. That in this case, the theory of Einstein will approach that of Newton, and Newton will give you a very good approximation. Not exact, but a very good approximation. So if you're really picky and you want to have the accurate measurements, you have to get that extra correction from the theory of Einstein. So that is really what we're talking about in here. Okay, Mr. Hubble, one of the problems of Einstein theory was the fact that during solving the equations of relativity, the universe was not stable. The universe should have collapsed a long time ago, immediately after it was basically born, because of the sheer amount of gravity. So Einstein, looked at the sky. Everybody looks at the sky and sees that the stars are out there. And he believed initially that they are fixed, stationary. So what he did is, in order to prevent his theory from predicting a collapsing universe, he introduced the constant. Okay, he called it the cosmological constant. Until Mr. Hubble was looking at specific kind of stars that he knows exactly the frequency that they emit with it. They emit the radiation with it when they go into a stage of supernova. Then he noticed that those frequencies that are emitted are shifted toward the red from the faraway galaxies. So he did a lot of measurements and he concluded that the universe actually is expanding. And he actually called Einstein to come to the observatory here in Mount Wilson, and he looked at it and he said, wait a minute, then that there is no need for my cosmological constant. And he actually called it my biggest blunder. The biggest mistake I made in my life, basically. There is no need for it then. If the universe really is expanding, that is good. All is good. The trouble with this is, in the 1990s, other observations basically concluded that that constant actually is needed, that the universe actually is not accelerating, is not expanding, but rather it's accelerating. So the mistake of Mr. Einstein was actually not a mistake after all. Even with that thing that he admitted as being a blunder, actually turns out to be something right in a sense. Okay. Of course, Penzias and somebody else were working on the, I forgot the other name, Enrico Penzias and the other one. Anyway, they were doing actually observations. They were trying to look into the sky and collect basically measurements, and they noticed that something was wrong with their data because they needed to calibrate the antennas. They needed to calibrate the antennas. So they wanted to get a view of the sky where there is no radiation. So they looked aside, because at that point, if the universe, from the Hubble's observations, if the universe is expanding, so at some point it was in a condensed fashion. So the theory of Big Bang was really taking shape at that point. A lot of people suspected that the universe then was a point in space, was a point basically before space and time, and when space and time basically emerged, it expanded all of a sudden. So that's basically the Big Bang. But there was no confirmation for it. Again, Penzias were looking for something else, and he discovered that there is some radiation. He initially thought that it has to do with the cities that are in the pollution, basically radiation pollution that was from the lights and so on and so forth. And he believed also because there were some birds basically nesting in there and basically doing their business there. So they went and cleaned the antennas. Still, that radiation still was coming. So that was the radiation that was discovered, was a confirmation of the cosmic basically radiation that emerged, the signature of the Big Bang. So there was a Big Bang, there was an initial point from which everything emerged. And one of the explanations for it, to make things hold true, and it's still really a lot of people are working on it, is the cosmic inflation. It seems like the universe expanded so much initially and continues to do so, okay, at tremendous speeds that at that point took all matter with it until it cooled down, and the universe now is still cooling and it's still expanding. So that's basically how this thing can be explained. There is a lot of work still ongoing in this one. What causes that inflation is still a problem, and that's where dark energy comes into play. It seems like there is negative pressure, which doesn't make sense, at least from our daily experience. Negative gravity, okay? Something that opposes gravity, something that keeps the universe from collapsing on itself. So that was one thing. Then, of course, the general theory of relativity of Mr. Einstein that basically explains a lot of the things I mentioned earlier. And then there was this observation by Vera Rubin. She was basically interested only on specific kind of stars. And she noted the following, that the stars in the halo of the galaxy, because as you move away from the center of the galaxy, the stars needs to move faster and faster, because there are more and more stuff, including stars and intergalactic cloud gases and things like that, that are enclosed. So they attract the stars that are further away from the center of the galaxy. So they need to move faster in order to stay in orbit. Otherwise, they will be attracted. So she measured those velocities. There is no problem with it. So at this point, it's perfectly clear that it's in accordance with Einstein, and actually more with the Newton too, because you don't really need Einstein calculations for this one. So it was beautiful. Everything was fine until she hit the points where there is no more stars or stuff from the galaxy to be enclosed. Now she's in what is called the halo of the galaxy. She's outside of the galaxy, basically looking at some stars. So technically, now they are further away from the bulk of the galaxy, so there is no need for them to gain more velocity to stay in orbit. What happened in this case is, as a matter of fact, they should be moving slower and slower. Like, for example, the case of Earth moving faster than Mars, and Mars moving faster than Jupiter. It takes for Earth 1 year. It takes 2 years for Mars to go once around the Sun. It takes 12 years for Jupiter to go once around the Sun. So the point being in here is, the further away now, since you are outside of that bulk of stuff, they should be moving slower and slower. Instead, she found them moving faster and faster. As a matter of fact, they kept the tremendous velocity. She concluded then that there must be stuff that I can't see. There must be things that we can't see. They don't, and things that radiation from the other stars goes straight through. So that is what was dubbed as dark matter. Of course, she was hesitant because she was a woman basically going against in a field that is dominated by men. And also, and that's in her account, she's the one who she's talking about that. She died in 2016, basically, and especially going against the biggest names in physics. One of them is Newton, who predicted that the stars should be slowing down. So instead, she did not find that. So she was very hesitant, but then her observation was confirmed later on. And sure enough, that's basically how dark matter was discovered, that there are more stuff in the universe than what we can see. As a matter of fact, where you are seated right now, if you move your hand this way or that way, you're encountering far bigger amount of dark matter than ordinary matter. So that's really what it is. So at this point, part of the research is, in this room where I am at and where you are at, there is a lot of dark matter, okay, a lot. I mean, a huge amount. So the ratio of matter to that of dark energy and dark matter is about 4%. There is a book about we live in a 4% of the universe. The other 96% of the universe is we don't even know what it is. We have no idea. So the word dark in here doesn't mean that it's black. It means that we don't know. It's like mystery. That's what the whole thing. And then we're going to talk a little bit about the fate of the universe. And this has to do with the so-called basically curvature of the universe, the density of the universe. Is the universe basically has a positive or negative curvature? Is the universe is going to basically collapse back on itself or expand forever? Is it going to die basically on the which way it's going to end, or is going to continuously expand forever and ever and ever until every single star is far away from the other stars, until every single galaxy is away from the other galaxies. As a matter of fact, until every single electron and proton are away from one another, until nothing can be seen. I mean, that's basically one of the possibilities. So it's a big order. So that's basically what we're trying to understand. Okay. So again, in the 1920s, that's when Mr. Hubble was looking at doing some observations basically on the stars, and he was looking at this specific kind of basically stars that the kind of supernova, special type of supernova. The further galaxies, he noted, they're moving faster, and as a matter of fact, some of them move faster, at least the furthest ones, than the speed of light. So you think that the galaxy is moving further speed of light. It's not that. It's actually the space between the galaxies, the one that is expanding. So these two galaxies, one of them is sitting in here and the other one is sitting in here. They're not actually moving. It's the space between them, the gap between them, that is increasing. So that's really what the rationale now is. And that's one of the things we talked about last time when we talked about the observable universe. The observable universe is what we can see right now. The actual universe can be several times orders of magnitude bigger. So right now we believe the observable universe is about 13, 14 billion light years in each direction that you can see. So that's how basically the universe is. The actual universe could be a radius of at least about 50 billion light years or more. So there are more stuff in there that we can see. And the galaxies that are really right now on the edge of that horizon, they're going to fall shortly out of it, and we cannot see them because they're expanding at tremendous speeds. So again, he came up with a wonderful law that explains all of that. Now, when we talked about the local group of the galaxies, actually, this does not apply to them because gravity still plays a major role, and they can still attract to one another. Like, for example, Andromeda and our own galaxy, Milky Way, they're going on a collision course. But when you look at it on a bigger scale, the universe is expanding. Okay. So again, this is his observation. Again, that's because of the light. Basically, he was looking at he knows the intensity of those specific types of supernova. So if you know their intensity, you know their luminosity, how much they're supposed to give you energy, okay? And you measure their observable energy. You see how much energy they're emitting, okay? So you can estimate the distance. So that's how he did it, okay? Furthermore, you know what kind of radiation they're going to emit. So you know the frequency. And the frequency is supposed to be here. You find it shifted here. So indicating, and it's shifted toward the red, meaning that they're moving away. If they were shifted toward the blue, that means they are coming closer to us. But they are shifted toward the red. And the trouble with his analysis is, if we are looking at this galaxy, for example, this is where we are, and this is the galaxy we're looking at. This is moving slower than this galaxy that is further away, that's moving further and further. So the further away the galaxy is, the faster they move. So that's really the conclusion that he ended up looking at. And that's why Mr. Einstein, when he looked at the observation, actually he was invited to Mount Wilson. He was in Princeton, he was invited in here in Los Angeles to look at this observations and the different data and how the pictures that basically Mr. Hubble took. He thought that he made a mistake in adding that constant, okay? This is the Doppler effect, basically. We talked about this one when we did electromagnetism a long time ago, and actually we did sound too, that an incoming source, basically, of radiation, the wavefronts appear compressed, and they will shift toward higher and higher pitches, higher and higher frequencies. And when they're receding, they will appear expanded, basically. They will appear, the distance between a wavefront and wavefront will be bigger and bigger, longer and longer the distances. The wavelength in this case appear longer. So the frequency appears less and less. So if the color was supposed to be in this place, for example, in the spectrum, it's going to move closer to the red than the blue if it's moving away from you. That's exactly what's going on with the stars. So how will the spectrum of the moving towards us change? The wavelength of the light will be stretched, making it redshifted? No, that's not correct, okay? The wavelength of the light will be compressed. So if it's coming towards us, it's going to be compressed, okay? By the way, this analysis, this studies is not more so, at least all of the interest of Mr. Hubble. First of all, the biggest discovery he made was the fact that, because people believed at that time before him that the galaxy is the entire universe. Our own galaxy, the Milky Way, is everything there is. And the universe is about 100,000 light years across, which is big, which is tremendous. And there were some islands like clouds in them that were classified by Messier, and they were called actually Messier objects, that appeared to be clouds in the middle of the universe that people didn't understand. And when Mr. Hubble was looking at them, he saw that they made up of tiny stars, and those are actually galaxies of their own right. So all of a sudden, the universe, instead of being this much size, now bloomed and became so big. So that was another major discovery. So imagine yourself that you were told all of your life, for example, that, I don't know, for example, Riverside is the entire country. And that's how you grow up to know that. The Riverside is the entire world. And then all of a sudden you learn, hey, there is San Francisco, there is Dallas, there is other places, and there is Tokyo, as a matter of fact. So that's really how the picture basically changed in day and night. Okay, discussion then, and there's all kinds of interesting discussions around that time. So again, this is the Hubble law. Okay, the further away, the parsec here is a measurement of distances, which is basically how much you can see in the sky, and the higher the velocity. Okay. So the further they are, the faster they move. And this is the mathematical expression where this h0 is a Hubble constant, okay? The velocity is proportional to the distance. The further the galaxy, the faster it moves. So this is basically that, and the constant seems to be a constant number. There is some new research that is coming out recently about this Hubble constant. There are two kinds of measurements to it. And it seems like there is a discrepancy between the two measurements. But basically, this is one of the modern day basically studies trying to figure out exactly where is this discrepancy coming from. Again, this analogy is a textbook analogy into how you can explain the expansion. So if you draw dots on a balloon and you start blowing on the balloon, each and every one of those dots should be moving away from the rest of the other dots. That's basically in a nutshell how we explain the expansion of the universe. So what's going on in here is that the dots are not moving. What is moving in this case is the skin of the balloon expanding, becoming bigger and bigger. So in this case is this distance between the two dots, any two dots on the surface will be higher and higher, and that depends on basically how fast this expansion is. And again, the distance between this balloon, this point and this point is going to increase less than the distance between this one and that one, because there is more stretching. For example, between this dot and that one, there is more stretching happening. So it appears that these 2 points will move further away at a higher speed than these 2 points which are nearby, because there is less material between, there is less space between them to expand. So that explains this Hubble's law. Okay. So that is, if you wish, a model on how to represent this thing. Again, the Big Bang was something that was speculated because of the expansion. So if the universe is expanding right now, can we roll the movie backward now and find it? What was it before? If you do the movie backward and you basically reconstruct the universe backward, you will find that 13.7 billion years ago, it was in a singularity. It was a point in space. Everything was in a point in space. And then, for some reason, the universe starts expanding. And it's expanded so big to almost its current size initially. Okay? And it was still super hot at that time. Okay? It was still super hot. It took about 300,000, 400,000 years for it, during that expansion, for it to cool down so that the first light starts to appear to us. So before that, the initial inflation, we really don't know what's going on. We cannot know what's going on, at least based on electromagnetic observations, based on light, because light was trapped inside the universe during the early stages on. So immediately after the Big Bang, what happened was the universe was super hot, super dense, that nothing could escape it, including photons. And photons, or particles of light, is the only thing we can use to see the universe, to see anything, as a matter of fact. So during the early stages, we cannot see anything. Then the universe starts to cool down. When it cooled down, then the protons and the neutrons start to form, and the electrons and the first molecules cooling just to try temperature, so that the photons started to escape the pole of the big, basically, chunk of it. So what we can see now, what Mr. Penzias and his partner looked at, was this background noise from the Big Bang. Right now, in every direction. As a matter of fact, if you have one of these old TVs, antenna TVs, and you turn it on, you will see like fuzzy pictures. I don't know if some of you are probably have seen that or not. Probably most of you are too young for that. Some of you probably can relate to that. At least I can. I've seen that so many times before TV broadcast in. That was actually the background noise that we're talking about in here. But there is no other signal. So that is really what it is. So, and then the universe starts to cool down further until first big stars and probably bigger supermassive black holes formed, and then the galaxies start to basically form, and the universe is still as we speak right now. As a matter of fact, the observations from 1995 suggest actually the universe is not just an idea why it does this. Now from time to time it happens like this, and I know nothing is going on, at least from my end. Can you guys hear me? Make sure that you guys hear me first.
Yes. Yes. We hear you.
Okay, thank you. So let's continue this. So again, this is the expansion basically that was actually discovered. Okay. So continuing expansion of the universe is another proof for the Big Bang. Measured cosmic background radiation, that was the one that and measurements of elements abundance predicted before measured. So, in other words, the presence of hydrogen and helium, at the ratios they are, it is really an indication of how they formed initially. So the protons that formed the hydrogen first, and then the initial reactions that formed the helium. Because if the universe existed before for a long time and continuously, there is no reason why this too will be the abundance and other elements would not. So the process of how elements are forming is an indication also of there is a starting point and how it started actually for it. So everything seems to confirm that. Okay. So when did this happen? I know some of, not 7,000 years ago anyway. Okay. So that's not true. That's not when the creation. I know some of the fanatics somewhere they will argue that. Not 100,000 years ago either. That's not when the first basically man or woman walked on Earth. Yes. Okay. Not 5 billion years ago when the solar system basically formed, when the sun was formed. So it happened before that, 13.7 billion years ago. Okay. So that's when it happened. So the sun really is not a first generation star, and indicated by at least the stuff that is on its planets, including Earth. Okay. Okay, so these are the two guys, Arno Penzias and Robert Wilson. That's the other name escaping me. Okay, they are the ones who basically discovered the cosmic background noise or radiation. Okay. So, and they discovered it basically with this antenna, and as I was before saying, I mean, they really discovered it by accident. Later on, it was mapped, and this is how the cosmic background radiation looks like right now. So the furthest that you can see from the early, basically, universe. So this is the baby universe, if you wish. So again, in order of elements, from fusion of lighter elements to the most dense one. So that's basically how that's going to support that. So 75% of matter, at least in the universe initially, was hydrogen. 25% was helium, okay, and 1% or less than 1% of traces of other elements. If you see first generation star, this is how much they are made up of, okay. Some of the small stars that we mentioned last time, for example, Proxima Centauri, most likely has this composition around it too, okay, because of the fact that it's a small star. So it must have existed a long time ago, or at least if it formed recently, but it has also the similar composition here. One of the things that we do when we observe stars, actually, we try to determine the ratio of, based on spectral analysis of this ones, to determine what generation they are. Because they will tell us if they could harbor basically life around them or not, because if they are first generation, most likely they don't have planets that do have life around them. So there is interesting studies in here related to these things in here. So, but the fact in here is that this is still the most dominant basically ratio in the universe, indicating that this is how they formed. So this is the signature basically of the Big Bang too. I'm sad to hear that at least some people still don't believe that. And when you say theory, when you attach something to theory, they think that this is some sort of an opinion. We argued that in the beginning, that a theory is actually an abundance of evidence to support basically a construct, a structure, if you wish, in science. Okay, so it's not, and it's not really a theory anymore. Okay, it's not in a sense. How should I say? It's not an opinion. It's not like this is my theory when you go to when people start to giving all kinds of left and right opinions. So there is a lot of evidence for this. So these are some of the basically indications for it. Again, I mentioned the fact that the relativity brought into perspective this concept of space-time continuum, and it was able to explain a lot of the things that we see in the universe that otherwise could not be explained. Okay, one of them, for example, is the precession of Mercury and other observations. So it explains the things that Newton was able to explain. It goes beyond that, and basically explains, among other things, how this universe basically is sustained and the formation of black holes. As a matter of fact, Mr. Einstein himself did not really believe that such atrocities could exist. I mean, although his equations led to them, but he didn't think that they're going to be observed, and sure enough, they are observed, actually. This is one of the things that we know. The theory of relativity is based on this principle of equivalence, meaning that we're sitting right now under gravity. We can measure gravity. We can measure Newtonian gravity that Mr. Galileo has measured, 9.8 meter per second squared. So this we can do. Okay, anywhere in here on Earth, we can feel it. What his argument is the following. There is really no distinction between an accelerated reference frame and one that is sitting under gravity. So that they are identical. So in other words, if you're sitting, for example, in a what is this one? I was going to say spaceship. Yeah, spaceship. Thank you, Sherry. In a spaceship, and all of a sudden, I mean, if it's not moving, you wouldn't tell. I mean, you know that you're not moving. So, or if you're moving at constant speed, it's the same thing. So think about your cup of coffee, for example, where you're cruising at constant speed. You look at it, and it sits next to you, not spilling. You can take it and actually drink it comfortably, no problem. But if you do a sudden acceleration or you hit brakes, then you can tell you're moving because of the fact that the cup of water now is shifting one way or the other, okay? And your body also will feel the acceleration and the deceleration. So if you are standing still in a spaceship and the spaceship is not moving, let's say, for example, you're enclosed in it, you don't see nothing in it, okay? All the windows are covered, then, hey, you don't know that you're moving at constant speed either. And the only reason, as a matter of fact, what could have happened is you could argue that even if it's moving at constant speed, because again, you can take your cup of coffee, you can drink it, you can put whatever is going to stay in its place. So you're sitting still. And even if you're looking at the window, there is no reason for you not to believe that the entire universe is being dragged in the opposite direction. It's the same thing. Okay, there is no experiment that makes a distinction between the two. However, if you're accelerating, then everything is different now. You can feel the emotion, number one. Number two, also, you cannot really tell if you are actually sitting on Earth, being pulled by gravity G, or actually the spaceship that you're moving on is moving with the acceleration G. It's the same thing. You will weigh yourself, and you will find, let's say, for example, you weigh 180 pounds, you're going to weigh 180 pounds regardless, okay? If you weigh, for example, if your mass is 70 kilograms, multiply 70 kilograms times 9.8, you're going to find a number. And if you're accelerating with the same thing and you stand on the scales, you're going to get the same number. So that's really the idea behind it, okay? So that's the point for it. Now, if the spaceship is moving at constant speed, and you take two masses, a lighter mass and a heavier mass, a hammer and a feather, okay? And you let go of them, and if you're not moving, there is no gravity, you're in empty space, they should stay where they are. Everything should stay where it is, okay? Including you, including everything. But now, if you're moving, and you have them in your hand with constant speed, and you let go of them, they will keep moving with constant speed, and the ship will move with constant speed. So in this case, they will stay in their place either. Same thing. But if you do the same experiment on Earth and you let go of them, they will fall toward the Earth. Okay? The only reason the feather falls later is because of the fact that there is air resistance. So assuming that there is no air resistance, they will fall at the same speed together. Okay? Now, if you are in empty space, and the ship accelerates and you let go of them, they will fall also toward the ground because the ground is rushing to meet them, accelerating toward them. So when you let go of them, yes, they were moving with the same speed as you are and the ship and everybody else, but the minute you let go of them, they are not being accelerated, they are not being dragged with the rest of the everything, the container, everything contained in that spaceship. So what happened in this case, the ground would come and meet them, and they appear to you that they are falling down due to some sort of gravity. So that is really the principle of equivalence that Mr. Einstein basically argued with, and was able to basically, based on which, build his theory of general relativity and make the case for it. So an accelerating reference frame is no different than force of gravity. That is really the real rationale behind it. That is really the whole idea in here. So what I feel like an acceleration for the Earth going around the Sun, being accelerated by Newton's force, F equals to big constant times mass 1, mass 2 divided by the radius squared, is nothing but the acceleration, because when you go around, you're accelerating actually, of v squared over r. Okay, same thing, solves the problem. Okay, so that is, so it's not a force that causes the planets to go around the Sun. It's not a force that is holding you toward the Earth. It's not the force of gravity that does that. It's actually the bending of space-time and the fact that you have to go through a space to go around in space-time, not space only, in this curvature, to stay where you are around the Earth, because the Earth makes a big dent in this space-time continuum, and actually you are moving around the Earth and around with that velocity to keep you in place. So it's the geometry that dictates the gravity, not a force of some sort. There is no need for a force at all. So that's really the biggest reasoning that Mr. Einstein have argued. This is the principle of equivalence that I meant about. So when you do an experiment, for example, when you throw a rock on Earth, it's going to go on a projectile. And if you do it on an accelerating spaceship, it's also going to fall a projectile. For you, did the gravity cause it, or did the accelerating reference frame do it? They are equivalent. Whichever way you look at it is the same thing. Now, if this is moving at constant speed, now it's not moving at constant speed, so it's accelerating actually. When it's accelerating, it will feel that way. If it's moving at constant speed, it should go straight as a line in here, because everything is moving in the same direction with the same speed. But if it's accelerating, now it was in contact with the spaceship, it lost contact with it, there is nothing to drag it with that velocity now. So it's going to stay in its path, and it's staying in a straight line, but the ship, wall, and everything is moving to meet it. So it appears to you that it is bending in a parabola. So there is no need again for a force. All you need is geometry. Okay. So again, this is for the light. It's the same thing. So light bends for the same reason in an accelerating frame for that reason. So if the force of gravity is equivalent to the accelerating reference frame, so why can't we believe that light will bend under gravity? So that's his whole argument. Then the conclusion of this is light, if it passes through the Sun, which is a big object, by the way, it does the same thing with any object. It doesn't matter which object that is, but the Sun, because of the sheer mass, when you do the calculation, the bending will be significant. So if you know a star is here, for sure, it will appear as if it's in this position, okay? So if the Sun is hidden from you, and you know the position of the stars in the night, because of the constellations, if you guys remember, during a special when the Sun goes around, when it's during a solar eclipse, we will see the stars that we normally see at night. So we know the position of that star, where it is. But instead of seeing it where it's supposed to be, we see it shifted by a big, I think almost 1.5 arcs. Okay, so we see it shifted. That's exactly what was observed in 1919, May 26, 1919, and that's what really prompted Mr. Einstein to fame, is this confirmation when there was a solar eclipse. I think Edinburgh is the one who did the, what is his name? Eddington? I forgot his name. Eddington, I think, is the one who made the case for it, and he started. And when Mr. Einstein was told about it, hey, your theory was confirmed in this observations. He didn't really, he said that the theory itself is so beautiful, and if God missed on it, I think he missed on a great opportunity, because he thought that the theory is too beautiful not to be right. That's really his argument in here. One of the arguments of physicists nowadays is for any theory, when you do all of the things that meets it, namely the arguments for it, the observation that confirm it, and everything else, they really think that the beauty and the symmetry should be something to be considered in one of the founding principles of that theory. I don't know. Probably so far we've been lucky to find beautiful and symmetrical theories, but down the road probably things are not as beautiful, at least from our perspective. Maybe they may be ugly, so that's the thing. Anyway, same thing with time, actually. Time actually, because of the fact that time changes, and I mentioned the fact that time for a moving frame is different than that of a rest frame. Same thing because of the acceleration. Now it's higher near the source of the acceleration, so time will actually slow down near a source of high gravity than one that is further away from it. And this is something that was actually you can where are we? Talking about dark matter already. Yeah, one of the things that is, for example, observed in the you can make the case for it from the redshift of the light that is emitted by stars, because big stars, they have big masses, so as the light escaping from it, the periods then tend to be longer, meaning that the frequency is less. When the frequency is less, they shift to the red too. Okay. I mentioned dark matter and how it was actually discovered. Dark matter is, we don't know what it is right now really, but we know there is abundance of it. The problem with it, it doesn't interact with with electricity and magnetism. We know that for sure. So light does not interact with it. Electrons do not interact with it. That's why when you put your hand through anything, you can't feel it. The reason why you feel the air, the reason why you feel your other hand is because you have electrons in this hand interacting with electrons in the other hand. The reason why you hear me is because there are electrical impulses that basically are pushed back and forth with the air in your ear, and then it goes and interpreted in your brain. So because of the electrons, you do all of this. You see something in here because of the electrons that you have in your basically retina. So what we do on a daily basis interact with are actually electrons. Electrons are tied to protons and neutrons, and that is what ordinary matter is. The reason why my hand cannot go through is because of this interaction. Now, if these things don't interact with electricity and magnetism, and that's how electrons interact. So my hand is now going through them without really feeling them, without really being interrupted by them. And the same thing, they could be going through me without being interacting with it. That's one thing. The other thing, I cannot see them, I cannot smell them, I cannot hear them, but they are with abundance where we are right now. So you walk through them, you cannot interact with them, you cannot see them, and they're basically as if they are not there. So that is really what it is, okay? So it's not imagining things. It's not really something that, but that's the point of it. Okay, that's basically the observation that what it led to. So we don't know what it is. So the reason why we call it dark is because we don't know it. That's all. It's like a mystery. So again, that's the argument. We cannot walk in the wall because of that, but we can walk through it because it's made up of other things. Again, it doesn't interact with electricity and magnetism. It doesn't interact with strong forces. It doesn't interact with weak forces, but it interacts with gravity, and that's how we discovered them. Dark matter seems to interact with gravity. And because of the changes in the velocity that were expected and were not found, so we know it attracts other stars, and the fact that the stars now are further away from the galaxy, they need to keep moving fast and fast so that they don't collapse on the center. They don't, so that they stay in orbit. So they are attracted by this dark matter. Everything in the universe is attracted to dark matter. Okay, so that's the problem with it, but not anything else. Again, this is the galaxy. Take any galaxy. This is our own galaxy. This is what you see. This is what the rest of the galaxy is actually. The halo of the galaxy is all of these things around it. That is where dark matter is for the most part, because there is no regular matter. And here there is regular matter that somehow is being collapsed in here, but the halo of the galaxy is made up of all of these things in here. See how much the stuff there is in there? So what it is really, at this point we're studying it, we don't know. There are some candidates, as a matter of fact, from the standard model, but they're still candidates, so we're not sure if they are the ones or not. So that's basically how it was believed, that dark matter also, at least from a gravity perspective, behaves similar to matter, but we don't know in terms of electrostatic forces. That's probably why it's not sitting together like the regular matter, because it's attracted by other forces. Okay, how are we doing on time? We still have a few minutes. Dark energy is really what's causing all of this in the universe to expand. Okay, we don't know what that is either, but it's tremendous quantity of it too. 76% of the universe is actually dark energy. Okay. Again, the reason why we call it dark is because we don't know what it is. So I don't know what that thing is. We know it's there by an abundance. Here are the ratios. 73%, I'm sorry I said 76, 73% of the universe is dark energy. 23% is dark matter. That leaves you with 96% of stuff that we don't know what it is. The rest of it, basically about 4% is hydrogen and helium, and the other stuff is basically the rest of everything else, okay? Hydrogen, that's intergalactic clouds, basically, intergalactic stuff. So actually, we sit really about 0.03% because we're made up of H2O, mainly water and other elements in us. So that's basically where we are right now, okay? And that also makes up also the planets and the universe, the rest of the universe. So there is actually an interesting book I still have about the 4%, where is the missing 96%? That's really interesting question. I mean, think about this the other way around. Let's say, for example, there are other people who are living right now, or at least other matter and dark matter. They would not really care about the 4% missing because they know that they have the 96% of the universe. That's really amazing, okay? Again, I mentioned the universe is really going to have two possibilities. Right now, we know, actually, this is an outdated study. The universe is expanding, so it's not going to collapse on itself, okay? So there is only one scenario, which is the universe is going to continue expanding, okay? Till it runs out of energy, until the last photon goes puff, and basically we don't have any energy left in the universe. For you who are interested, you can read the story, and again, I mentioned it before probably, of Isaac Asimov on basically the last question, okay? Because the universe will be dying and will be running out of photons, running out of energy, and basically that's the end of it. Okay, so this is, on this note, we're going through, there is no question today. And I'll see you guys. You have the review. It should be available today at 10 a.m. Or is it available already? I'm not sure. I think I made it so that it will be available after class. And if you have any questions, please reach out to me. And good luck with the rest of everything else, and for this class and for any other class that you're taking.
I have a question.
Yes.
Sorry, I was late because I had workers here laying concrete in my backyard.
Hold on. Let me stop the recording first, okay?